Multivariate normal distribution. In the multivariate case where x is d-dimensional and normal distributed, we have p of x which is equals to 1 divided by 2 pi to the d over 2 times the absolute values of sigma to the 1/2 times the exponentials of minus 1/2 times x to the mu x minus mu to the transpose times sigma inverse of x minus mu. And we write x, which is approximately as the ND of mu sigma, where mu is the mean vector and sigma is the covariance matrix. See figure 5.1, where this ND I think is normal distribution. And just as x minus mu to the square divided by sigma square is equals to x minus mu times sigma square to the inverse times x minus mu. So is the squared distance from x to mu in a standard deviation units, normalizing for different variances. In the multivariate case, the Mahalanobis distance is used as follows. Mahalanobis distance is equals to x minus mu to the transpose times sigma inverse of x minus mu, and x minus mu to the transpose times sigma inverse of x minus mu is equals to c squared is the d-dimensional hyperellipsoid centered at mu, and its shape and orientation are defined by sigma. Because of the use of the inverse of sigma, if a variable has a larger variance than another, it receives less weight in the Mahalanobis distance. Similarly, two highly correlated variables do not contribute as much as two less correlated variables. The use of the inverse of the covariance matrix thus has the effect of standardizing all variables to unit variance and eliminating correlations. Let us consider the bivariate case where d is equals to 2 for visualization purposes. See figure 5.2. When the variables are independent, the major axes of the density are parallel to the input axis. The density becomes an ellipsis if the covariances are different. The density rotates depending on the sign of the covariance or correlation. The main vector is mu to the t, which is equals to mu1, mu2. And the covariance matrix is usually expressed as the following. Sigma equals to sigma 1 to the square. This is on the left and the top side. Rho times sigma 1 times sigma 2. This is on the right and top side. Rho times sigma 1 sigma 2. This is on the left and the bottom side. Sigma 2 to the square. This is on the right and the bottom side. The joined bivariate density can be expressed in the form Cx as 1, that is the p of x1, x2 is equals to 1 over 2 times pi times sigma 1 times sigma 2 times the square root of 1 minus rho square, then times the exponentials of minus 1 divided by 2 times 1 minus rho square times the following terms: z1 to the square minus 2 sigma times z1 to the square minus 2 rho times z1 times z2 plus z2 to the square, where zi is xi minus mu I then divided by sigma I, where I is 1 or 2, the index, because they are two different kind of variables, and thus zi are standardized variables. This is called z normalization. And remember that z1 squared plus 2 rho z1 z2 plus z2 squared is a constant. For rho whose absolute value is less than 1 is the equation of an ellipse. When rho is greater than 0, the major axis of the ellipse has a positive slope, And if a rho is less than 0, the major axis has a negative slope. In the expanded Mahalanobis distance of equation 5.11, each variable is normalized to have unit variance, and there is the cross term that corrects for the correlation between the two variables. The density depends on 5 parameters: the two means, the two variances, and the correlation. Sigma is non-singular and has positive definite, provided that variances are non-zero and the absolute values of rho is less than 1. If rho is plus 1 or minus 1, the two variables are linearly related. The observations are effectively one-dimensional, and one of the two variables can be disposed of. If rho is equal to 0, then the two variables are independent. The cross term disappears, and we get a product of two univariate densities. In the multivariate case, a small value of the absolute values of sigma indicates samples are close to mu, just as in the univariate case where a small value of sigma square indicates samples are close to mu. Small absolute values of sigma may also indicate that there is high correlation between variables. Sigma is a symmetric positive definite matrix. This is the multivariate way of saying that the variance of x is greater than 0. If not so, sigma is singular and its determinant is 0. This is either due to linear dependence between the dimensions or because one of the dimensions have variance 0. In such a case, dimensionality should be reduced to get a positive definite matrix. Methods for this are discussed in chapter 6. If x is approximately equals to the ND of mu sigma, the normal distributions of mu and sigma, then each dimension of x is univariate normal. The converse is not true. Each xi may be univariate normal and x may not be multivariate normal. Actually, any k less than the subset of the variables is k-variant normal. A special naive case is where the components of x are independent and the covariance of xi xj is equals to 0 for I not equals to j, and the variance of xi is equals to sigma I squared for all I. Then the covariance matrix is diagonal, and the joint density is the product of the individual univariate densities. That is, p of x is equals to the product of pi of xi, where the multiplication is for index I starting from 1 to d, and which is equals to 1 divided by 2 pi to the d over 2, then times the pi of sigma I, where the multiplication is, again, multiplying for all index I starting from 1 to d, then times the exponentials of minus 1/2 times the summations of the following terms. The square of xi minus mu I divided by sigma I, and where the summations is summing for all index I starting from 1 to d. Now let us see another property we make use of in later chapters. Let we say that x is approximately as ND of mu sigma, and w is in R to the d, then w transpose times x is equals to w1x1 plus w2x2 plus w3x3 and so on plus wdxt, which is approximately equals to the normal distributions of the following two terms, w transpose times mu and w transpose times sigma times w. And we're given that the expectations of w transpose times x is equals to w transpose times the expectations of x, which is because expectations of x is mu, so we substitute that as w transpose times mu. Again, the variance of w transpose times x, if we expand the term by the definition, that would be the expectations of the square of w transpose times x minus w transpose times mu. If we expanded that, it would be the expectations of the following multiplications of the following two terms. First term, W transpose times X minus W transpose times W. The second term is the same. If we combine these multiplications of the two terms instead of the expectation, there will be the expectations of W transpose times X minus mu times X minus mu to the transpose times W, which is equals to W transpose times the expectations of the X minus mu times X minus mu to the transpose, then times W. So by the definitions of the sigma, the expectations of X minus mu times X minus mu transpose is equals to sigma. So we can reduce the following terms, the formulas with a simpler one, that is W transpose times sigma times W. That is the projection of a d-dimensional normal on the vector W is univariate normal. In the general case, if W is a D times K matrix with rank K less than D, then the k-dimensional W transpose times X is a k-variate normal. That is, W transpose times X is approximately by nk of W transpose times mu and W transpose times sigma times W. That is, if we project a d-dimensional normal distribution to a space that is k-dimensional, then it projects to a k-dimensional normal.